Okay, in the last part of this week, I am going to talk about the symmetry groups of a mechanical system. Now, this topic is slightly technical and I am going to leave it as an optional topic for the examination. Okay. So, those who do not know what groups, mathematical structures called groups are, you can skip this chapter. Okay. Now, let me begin first of all by the recap of what we did in the last class and talk about the infinitesimal canonical transformations. Okay. So, if you have an infinitesimal canonical transformation which we abbreviated as ICT, remember we had two ways of looking at that particular transformation. One was an active view and one was a passive view. In the passive view, we assume that, or we view the entire phase space as is, the points remain where they are. All that happens is the coordinate system that we are using to describe these points, they change. Okay. So, when the coordinates change, points are exactly where they are. If you have a function defined on the phase space, the function also will retain its value at the same point. Another view, the active view, is when we think that, or we view this transformation as transforming the points to new points. Okay. So, in this case, if I say we have a ICT and in the active view, your point A here, the point A here will be mapped to the point B here, okay. And the coordinates of the point B will be eta plus some delta eta, because remember it is an infinitesimal transformation. So, the change in the coordinates or change in the point is also infinitesimal. Okay. And we remember how to write this infinitesimal change. Now, if I had a function defined over this space, then what happens to this function under the transformation? So, we will talk about change in the function, because point has shifted from A to B, how much is the change in the function? So, in that case I will write delta u, change in the function, as value of the function at B minus value of the function at A, okay. And that of course, by coordinate transformation or the transformation, we know that u at eta plus delta eta minus u of eta, and then you do a standard Taylor expansion for this and you would get gradient of u with respect to eta multiplied by the displacement, that is delta eta, okay. And that now we can write as, we already know delta eta by a transformation whose generator, or by ICT whose generator is capital G, is given by j times delta or gradient of capital G multiplied by that small parameter epsilon. Okay. And then you can immediately see from the definition of Poisson brackets that this is exactly equal to epsilon times the Poisson bracket of u and g. Okay. So, this is a simple formula. Once we have an active view of the ICT, when you go from point A to point B under the transformation, there is a change in the function, and change in the function is exactly given by epsilon times the Poisson bracket of u and g. Now, if I want to do the same thing for the Hamiltonian, instead of a function I want to calculate change in the Hamiltonian, but you see what happens when I change the frame, then the Hamiltonian also changes. What I mean is, the remember all this while we have been talking about Hamiltonian of the system in a given coordinate system. Clearly, the change in the function u will be 0 if Poisson bracket of u and g is 0. Okay. So, we will say function u is invariant under the transformation. Okay. Now, we want to do the same thing for the Hamiltonian. Remember, when I talk about Hamiltonian of the system, we do not refer to a particular function, because the function which is called as Hamiltonian changes the moment you change the coordinate system, okay, or you make a transformation to new canonical variables. Unlike in the point transformations for Lagrangian formulation, whenever you make a point transformation, the value of the Lagrangian at a point does not change, but not here. Here the Hamiltonian function itself changes. So, if I want to see how much change is there in the Hamiltonian, what I need to do is not just do, if H is a Hamiltonian, not just do H b minus H a, but under the transformation point B is in the new coordinate system. So, I need to do something like Hamiltonian in at point B in the new coordinate system minus Hamiltonian at point A, but in the old coordinate system. Okay. So, that I am going to write, suppose H changes from H to K under ICT, then I will write delta H as change caused by not just going from A to B, but because the function itself changes. Okay. So, that will be H b, the Hamiltonian at point B, minus K of A. So, in the new coordinates, of course, the value of the Hamiltonian at A also would have changed. So, I would put that as K of A. Now, this we can immediately calculate, because K of A we know is equal to H of A plus epsilon times del G by del T. Okay. So, by putting that there, and now we have H b minus H a, which I can express as minus epsilon times H comma G, and then you have minus epsilon d G by d T. So, the net change in the Hamiltonian when you do a ICT or a transformation is this much. So, when will the Hamiltonian be invariant? We will call the Hamiltonian, or we will say Hamiltonian is invariant under a transformation when this change is 0, and that will happen when del G by del T is equal to minus of Poisson bracket of H and G. But now remember, if this happens, what does that mean? That automatically means d G by d T must be 0 along the trajectory of the system, and that immediately means G must be a constant of motion. Okay. So, let me write that in a neat form. If an ICT, infinitesimal canonical transformation, leaves your Hamiltonian invariant, then the corresponding generator must be a constant of motion for this mechanical system. Okay. Now, this of course gives you a great advantage or connection between symmetries and the constants of motion. Okay. So, or the conservation principle. Now, look at one example. I want to derive momentum conservation theorem. Okay. And in this case, of course, I would not talk about a particularly linear momentum, but the canonical conjugate momentum being conserved when you have a translation or when particular coordinate is absent from your Hamiltonian. Okay. So, let me take the generator of ICT as just P of k for some k. Okay. Now, what kind of transformation will it generate? So, we look at the change in the coordinates. Change in the coordinates would be delta q I, change in the q coordinate will be equal to epsilon times d G partial of G with respect to P I. But remember, G is nothing but just equal to P k for some fixed k. So, this is going to give you epsilon times j k, which means all the q I coordinates are unchanged except for q k, and what happens to q k? New q k is old q k plus another epsilon there. Okay. What happens to the momenta? Momenta are given by, or change in the momenta is given by del G by partial derivative of G with respect to q I, but q I is absent in G. So, this is anyway 0. Okay. So, this is a transformation where all canonical variables including the coordinates and momenta remain fixed except for one coordinate q k is translated. So, q k prime is translated by, or q k prime is equal to q k plus epsilon. So, when you have this, now look at what happens. We will say P k generates translations in q k. So, the statement is the momentum is generator of translation transformation. And when will you have the conservation principle? If H is invariant under translation in Qk, then what is conserved? Capital G is conserved, and capital G in this case is just Pk. There. So, you have the connection between, remember earlier we had a mathematical statement. What was the mathematical statement? If Qk is absent from capital H or Hamiltonian is independent of Qk, then Pk is conserved. There is no connection with the symmetry there. Now, we have made that connection with the symmetry, that if your system, and by that I mean the Hamiltonian, is translationally invariant in the direction of Qk, then the corresponding Pk is conserved. Okay? Fine. Let me look at some more examples. And once we have seen this one, the angular momentum in a particular direction, how about rotations? So, I will take an example of just one particle in 3 dimensions. Okay. Now, the standard coordinates there would be, natural coordinates would be the 3 Cartesian coordinates and the corresponding momentum. So, you have phase space has this 6 variables. Now, let me take one generator, and generator is defined as xpy minus ypx. Now, what happens? What kind of transformation does this generator generate? Now, the transformation of course can be found very easily. Once you have G, remember I use this formula. So, delta x is nothing but J times. So, delta x here would simply be partial derivative of G with respect to Px multiplied by small epsilon. In this case, I am taking that small quantity to be d theta. Okay. So, delta x will be, when you take a partial derivative of G with respect to Px, I would get minus y. Okay. Can you see that? Yeah. So, I will put that minus y there into d theta, and then similarly calculate delta y. Delta y will be equal to x times d theta, and then finally delta z would be 0 because Pz is not there in capital G. Fine. What about the momentum? Remember, this is not just merely a rotation in the ordinary space, this is a rotation in phase space. So, we are not only rotating x, y, z, but we are also rotating Px, Py, Pz. And what happens to delta Px? Change in Px is given by partial derivative of G with respect to x, and that immediately gives me this. And then of course, there is a minus sign because of that J matrix there. And then delta Py would be similarly Px times d theta, and there is no change in Pz. What is this? This is just a rotation about z axis. You immediately recognize this. Remember, if I make a rotation about z axis, what happens to the x coordinate? The new x coordinate x prime is x cos theta minus y sin theta. Okay. And now, if I take small theta, then cos theta becomes 1 and sin theta becomes theta or d theta, and then new coordinate x prime minus x is just simply equal to minus y times d theta. This is exactly what the rotation is. Fine. So, this is a rotation about z axis by an angle d theta. Okay. Fine. So, there. So, you have a one generator of, and then so the generator capital G, which is x p y minus y p x, I will also call this as L z, because this is the quantity that would remain invariant, and we know what this is. This is in fact z component of the angular momentum. So, I will call it as L z, and L z generates the rotations about z axis. What about L x and L y? So, L x would be x component of the angular momentum, and they also would generate rotations about x axis and y axis respectively. Remember, your L x would be so Lx would be ypz minus zpy, fine, and this would in fact generate rotations in yz plane, and similarly y would Ly would generate rotations in xz plane. Okay. And remember, these are rotations in phase space, which means it is not only rotation in xy plane, but it is also rotation in px/py plane, okay, leaving both z and pz constant. Fine. Now, the question that we would ask, there is nothing special about Lz, there is nothing special about Lx or Ly. How about if I take L dot n cap, where n cap is some fixed unit vector in the space? What kind of transformations this would generate? Okay. To look at that, we must go back to the geometry there, and if you recall, I am sure you must have done this in rigid bodies at some point, the rotation about some n cap axis. So, I have drawn n cap axis here, okay, and then there is a r vector which is given by this vector here, and when you rotate r vector about n cap, what it would do is it would trace out a cone about n cap, okay, and keeping the angle of the cone fixed as it traces the cone out. So, the here r would go to r prime if I have rotation by amount theta. And how do I express r prime in terms of r? Oh, there is a what is called as Rodrigues formula for that, and then Rodrigues formula is given by r prime is equal to r dot n cap times n cap plus r minus n cap times n cap dot r times cos theta, and then there is a last term which is r cross n cap times sin theta. How do I derive this formula? It is not really difficult to do. What you can do is you can start by dropping a perpendicular. So, you have this plane which is marked by the blue circle. Remember, blue circle will mark a plane. Now, in that plane you can drop a perpendicular. So, I can actually show you this diagram a little wider, and you can drop a perpendicular from here to this line, okay. And now you express. So, if I write this point as A, this point as B, and this final point as C, your r prime vector is in fact OA vector plus AB vector and plus BC vector, and then you express them in terms of all the standard known quantities there, which is just n cap r and theta. And if you do that, you will get this formula. I will of course ask you people to practice this again at home. Derive this formula. This formula is also given in Goldstein's book in the 4th chapter, which is on rotations. Fine. Now, look at what happens to this change. So, the change is given by of course r prime minus r, that is your delta r vector, and how much would that be? Remember, if I am taking a small angle, then of course I will approximate cos theta by 1 and sin theta by theta, or if I am taking the angle to be d theta, then sin theta sin of d theta would be d theta, okay. And you can immediately see this term here, n cap dot r times n cap will cancel with the first term here if you put cos theta is equal to 1, leaving you with r prime is equal to r plus the last term approximates to n cross r times d theta. Okay. So, what is the change here? The change is in fact d theta times n cap cross r. Fine. Now, let me write this in the form of, so this would be d theta. If I write n cap vector, I will write it here on the top. So, n cap vector, the 3 components of that are given by nx, ny and nz. Remember, it is a unit vector. So, then n cap cross r would simply give you nyz minus nzy, okay, and times I cap plus the remaining two terms. And now let me just look at the delta x component of it. So, that is the first component here. If I look at delta x component, that is going to be d theta times nyz minus nzy. And remember, keep in mind that we have found delta x here from what? From the rotation formula. Okay. Now, what I am going to do is I am going to derive delta x from a generator, as if it was generated by an ICT. Now, look at what happens. I will take the generator capital G, remember, to be L dot n cap, and in that case this of course evaluates to Lx nx plus Ly ny plus Lz nz. And now from here let us calculate delta x. What would I get? Delta x is nothing but small d theta multiplied by, remember it was delta u was nothing but epsilon times u Poisson bracket with capital G. We will do that here. So, change in x is a Poisson bracket of x into capital G, or a Poisson bracket of x and G multiplied by that small epsilon factor. Okay. Evaluate this. Nx, ny, nz are constant numbers, remember. What would be Poisson bracket of x and Lx? Now, what appears in Lx is ypz minus zpy. Now, x, you remember the fundamental Poisson brackets, x commutes with all these guys, all these entries. So, x commutator with Lx is going to be 0. What about x commutator with Ly? Now, Ly has zpx. So, let me write it here again. So, Ly is nothing but zpx minus xpz. Now, what will happen? X commutator with px, that gives me 1. X commutator with z gives you 0. X Poisson bracket with itself is 0 and x Poisson bracket with pz is also 0. So, this contributes one term which comes from Poisson bracket of x and px. I have written that here. Okay. So, from here I will get a contribution only when I take a Poisson bracket of x and px, all of that, and the same thing would happen in the last term. The Poisson bracket of x and px would give me a non-zero term, all of the terms will give you 0. That evaluates. So, ny times z, that comes from here. So, Poisson bracket of x and px is 1, that leaves you with z, and multiplied by ny, there you go. So, delta x is this. You see, the amount of change produced by L dot n cap in the coordinates is exactly same as a rotation by amount d theta about n cap axis would do. So, we identify this particular generator here as generator of rotation about n cap by amount d theta. Remember, I did this calculation only for delta x. You have to also check that from rotation formula, whatever delta y and delta z you get, and also p delta px, delta py and delta pz, all these quantities which are obtained from the rotation formula and from ICT, they must be same. Okay. I have just shown you one calculation there for delta x, but you have to do it for every other canonical variable. Okay. Now, so what happens here? L dot n cap causes the rotation about n cap, that we know. Now, if I take any vector function of q and p, then what happens? Remember the diagram there. I will just go back in a moment and show you this diagram. Remember, this diagram was about r vector, but it is just a vector. How about if I replace the same thing by f vector, some other arbitrary vector? Remember, the vector of course must be a function of the canonical coordinates or canonical variables, and then that also would rotate. Okay, fine. So how much change would be there in the vector function f? That also will be given by d theta times the Poisson bracket of f with the generator, and that generator here is nothing but L vector times n cap, and that will be equal to d theta times n cap cross f, that we know. Fine. Now we can look at all the other Poisson brackets that L generates or Poisson bracket of other quantities with the L vector, and you see f Poisson bracket with L dot n cap is n cross f. Fine. In the first go, I will choose for f vector L vector itself. If I choose L vector itself, that L vector Poisson bracket with Lz, suppose we choose f vector to be L vector and n cap to be k cap vector, that is the vector in the z direction. Then you get Lz here, and for f you have, and that is nothing but k cross L according to this formula, and if I calculate that, that would be minus Ly, Lx and 0. Okay. So, I get 3 Poisson brackets from here. What are those? Lx Lz must be equal to minus Ly. Remember, this L should be written in terms of a vector. Fine. So, comparing the components on this side to the right hand side, I get the first Poisson bracket, which is Lx Lz is minus Ly. What about Ly Lz? That is going to be Lx, and the third Poisson bracket is Lz with itself, and what will that be? That of course is 0. And similarly, you can start with this expression, but instead of using Lz, if I use Lx, I still get the new quantity, and then I will get Lx Ly Poisson bracket is Lz. Okay. So, I can write this in a neat compact form. There is a reason for doing that, and I will come to that in a moment. I can write this in a compact form, that Li Lj Poisson bracket is equal to epsilon ijk times Lk. Now, this epsilon ijk is called as Levi-Civita tensor, okay, fully antisymmetric tensor. And what is the value of epsilon ijk? Epsilon ijk, I will write again here in the corner, epsilon ijk will be equal to plus 1 if ijk, remember ijk can take values 1 to 3. If ijk takes values 1 to 3 in the cyclic order. So, all the combinations I is equal to 1, j is equal to 2, k is equal to 3, or I is equal to 2, j is equal to 3 and k is equal to 1, they all will give you plus 1. So, this is cyclic permutation of ijk between 1 to 3 will be equal to minus 1 if ijk are equal to 2, 1, 3. Remember, I have already permuted 1 and 2. So, after one permutation I get 2, 1, 2, 2, 1, 3. So, that is like non-cyclic permutation of 1, 2, 3 or a transposition of I and j, and will be equal to 0 if any of these two indices I, j, k, they have same value. So, epsilon of 1, 2, 3 is plus 1, epsilon of 2, 1, 3 is minus 1, epsilon of 1, 1, 1 is 0, epsilon of 1, 1, 2 is also 0, okay, because two of these symbols are same, it is 1, 1, 2. Okay. So, if I look at this particular symbol, then I can write this in a neat compact form. Li Lj is equal to sum over k epsilon I j k L k, and that also tells you one thing, you see. So, if you take the Poisson bracket, so let me put it this way. Lx, Ly, Lz are three functions defined on the phase space. When I take Nx Lx plus Ny Ly plus Nz Lz, I form linear combinations of these. Okay. Now, you construct a set of all possible linear combinations of Lx, Ly, Lz. What will that give you? A vector space. Okay. Now, on this vector space, now we are going to define this product. This product is a Lie product. So, think of this as Li, some sort of a product with Lj, and what does it give you? Epsilon ijk times Lk. This product is closed on the set of linear combinations of Lx, Ly, Lz. This structure is called as algebra. I will come to that in a moment in the next slide. So, now this one here also makes a statement about the symmetries and the constants of motion. So, because Lx, Ly, Lz are generators of rotation, if your system is invariant under rotation about Lz or z axis, then Lz is the generator, and because of symmetry Lz will be a constant of motion. And remember, if I have, for example, Lx is a constant of motion, that means your Hamiltonian is symmetric under rotations about the x axis, then you have Lx as a constant of motion. And if you have both Lx and Ly as constants of motion, remember Poisson theorem? Oh, then Lz, which is Poisson bracket of Lx and Ly, that also will be a constant of motion. Okay. So, if any of these two are constants of motion, then the entire L vector is a constant of motion. Okay. That is a great thing that comes out of this Poisson algebra there. Fine. Now, let me make this the whole idea into a formal idea. Remember, this is a little technical. This requires you to sort of have some idea of what mathematical groups are. Okay. Now, we have seen that the set of canonical transformations, all possible canonical transformations irrespective of whatever Hamiltonian that we are talking about, that will form a group, a mathematical group. And what is a mathematical group? Remember, it is a set on which some multiplication is defined, and multiplication is defined in such a way that the multiplication is closed, then it is associative. There is an identity multiplication. That means there is an element which we can designate as identity, and identity into any other element will give you that element. Okay? Just like 1 into any real number will give you that real number. So, 1 becomes an identity in case of set of real numbers. Now, what about, so the fourth property is that there is an inverse for every element in the group. Now, does our canonical transformation, all possible transformations, do they form a group? Yes, because look at product of two canonical transformations is again canonical transformation. And by product, what we mean here is you apply one coordinate transformation by one transformation and then apply the second one. When you apply two transformations in succession, it is like a conjugation of functions, then you have a product of two transformations. And will that be canonical? Yes, because remember the symplectic condition. Symplectic condition is transformation is canonical if the Jacobian matrix is symplectic. Okay. So, when you apply two transformations one after the other, that is equivalent to multiplying two symplectic matrices. But we already know that the product of symplectic matrices is another symplectic matrix there. So, this property is satisfied. What about associative? Oh yes, it is associative, and we have already seen the identity transformation. Remember in the first lecture in the last week when we talked about generators, the second variety of the generators, which is function of old coordinates, new momenta, that generates identity transformation. So, we already have identity transformation, and every canonical transformation Of course, they are all invertible transformations, otherwise we would not do such a coordinate transformation, okay, or canonical variable transformation. So, there is a inverse for this. So, the set of all canonical transformations on a given phase space, they anyway form a group. Now, what is the symmetric group of a Hamiltonian? So, on this phase space, suppose you have a mechanical system which is described by some Hamiltonian, and now look at all those canonical transformations out of set of all possible transformations, only those ones which leave your Hamiltonian invariant, and that set is called as the symmetric group of the mechanical system. Okay. So, every canonical transformation that leaves Hamiltonian invariant, put that in a set, we can show that this set will also form a group, and which of course will be a subgroup of that bigger group of canonical transformations, and that group is called as the symmetric group of the mechanical system. Okay. And why do we want to find such a symmetric group? Remember, the moment you find the symmetric group, you now have an association with constants of motion, which means finding a symmetric group of a mechanical system is very useful in actually solving the problem. And what I am going to do in next 2-3 slides is take a few examples just to illustrate this idea. Okay. We are of course not going to go into the theory of the mathematical groups that appear here. They are called as Lie groups, and this product here which is Poisson bracket, we will not that is called as a Lie bracket, but we will of course not go into the entire mathematical theory. I am just going to give you a basic idea what we are talking about here. Now, such a big group is actually parameterized by, so the elements themselves are parameterized by few parameters. Okay. And I will start with an example so that this idea becomes clear. Take for example, a spherically symmetric system. In a spherically symmetric system will be invariant under all possible rotations. So, I can keep things very simple. Go back to your example of one particle in just the 3-dimensional space. Phase space is 6-dimensional, and in this case the system is spherically symmetric, say. Now, that means if I take a rotation about any axis, then the Hamiltonian is left invariant. Okay, this is what we have. Now, so any axis. Now, this group is of course called as SO3 group. So, set of all rotations in the ordinary space, ordinary 3-dimensional space is actually called as SO3, and you can see what is contained in this SO3 contains all the rotations. Okay. Now, look at one individual rotation from this set. How many parameters are required to specify this rotation? Now, this rotation has an axis and the amount of rotation. Remember, axis is given by a unit vector in that direction. Once you have unit vector, you need only 2 direction cosines to specify the direction of that vector. Okay. And the magnitude is of course unity. So, that is your n cap vector, and the third parameter is the amount of rotation. Okay. So, all that you need are 3 parameters to specify a single rotation. Now, do these parameters continuously change? Let me take one by one. Say for example, if I am talking about the rotations about some fixed axis. Now, what would be identity transformation? No rotation. The amount of rotation or angle of rotation is 0. That is your identity transformation irrespective of the direction of n cap. Now, you start increasing theta by little by little. See, you got a ICT. Okay. Once you have axis and you do infinitesimal rotation, and to get into a finite rotation, all I need to specify is the actual amount of rotation there. So, the theta parameter can be continuously varied and you get different rotations. What about the direction of the n cap vector? Oh yes, I mean every direction there is a valid direction of or valid axis of rotation. I can infinitesimally change the direction of the axis of rotation. So, all these 3 parameters actually can be continuously changed, and that is why it is called as a 3 parameter group. That is also one of the reasons why this is called as 3 parameter group. Now, which 3 parameters? So, we have already discussed these 3 parameters. Which generators would generate these rotations? So, the rotations are generated by a generator L dot n cap. Now, you see those 3 parameters actually can appear in this expression here itself. There are already 2 of them there in the n cap, the third one will come in the form of d theta. Okay. Now, so these generators themselves are infinitely many, and all these generators, as I was telling you earlier, will form a vector space. That is, it is a set of all linear combinations of Lx, Ly and Lz, making Lx, Ly, Lz as a natural basis of that vector space. And then we have this Poisson bracket, which I will treat as a multiplication on this space. Remember, under Poisson bracket or this multiplication is closed operation, it is a binary operation, but it is a closed operation on this vector space. So, when you take a Poisson bracket of 2 generators, say I have 2 separate n cap and n cap, m cap, and I take L dot n cap and L dot m cap. They give me 2 different generators. If I take a Poisson bracket of these 2, what would I get? I would get another generator, and that can be expressed as some A times Lx plus B times Ly plus C times Lz. Okay. So, this structure together, so it is a vector space with an additional multiplication defined over it. Multiplication has some properties with respect to addition too, and then all of this is called as a Lie algebra. Okay. Together, so 3 generators, they forming a vector space under addition, then a multiplication which is closed and have certain properties. This all thing together is called as a Lie algebra, and the entire structure of that Lie algebra is contained in this statement here. So, you have 3 bases, you take pairwise Poisson brackets and then write it as linear, because it is a vector space, you can write it again as a linear combination of basis vectors, that is linear combinations of Lx, Ly, Lz, and these coefficients there, they are called as structure constants. Okay. So, what are those structure constants in this particular case? We already remember, we already have this expression, and this Cij case for this group is exactly equal to epsilon ijk, and that epsilon being the Levi-Civita tensor. So, the structure of this Lie algebra, which is encoded in these structure constants there, actually decides the complete nature or complete structure of your symmetry group of the Hamiltonian. So, all that I really need to do is study the infinitesimal canonical transformations which leave my Hamiltonian invariant, or which leaves your system invariant, and from that we can generate the entire group, symmetry group of that particular system. Okay. I will give you one more example. Finally, this is the last example that I will do. Take a harmonic oscillator in 2 dimensions. In the harmonic oscillator in 2 dimensions, the Hamiltonian is px square plus py square by 2m and plus some half m omega square times x square plus y square, and we can immediately see the potential is like a cup in the xy plane. Now, once you have this case, one of the symmetries is trivially obvious. What is that? Rotation about z axis. So, you rotate about z axis x square plus y square remains always constant, okay, which means this entire expression will be left invariant if your one of your generators is Lz. Okay. So, look at the constants of motion of this, that Lz must be one of the constants of motion. I will list out all the possible constants of motion here. One is of course energy, that is because the Hamiltonian is independent of time. So, we remember this theorem. Now, the second one is the angular momentum, which I was just telling you about, and I have just written it as L because we are considering only 2 dimensions. So, there is no Lx Ly. So, L, which is defined as xpy minus xpx, angular momentum is also a conserved quantity. Now, look at this very interesting thing. These two harmonic oscillators, one in the x direction, one in the y direction, I can actually separate this as 1 over 2 m, and then you have px square plus m square omega square x square, and plus another term for, let me call this as piece as hx and this piece as hy. What do you get? Hx and hy behave like two separate oscillators which are uncoupled. So, if I give energy to one oscillator, that energy is actually conserved. There is no mechanism by which the energy in one degree of freedom, that is x, can be transferred to energy in the other degree of freedom, which is in the direction of y. That you cannot do. So, hx, which I am going to denote by A11, is a conserved quantity. Similarly, hy is also a conserved quantity. And finally, and that happens because they are uncoupled oscillators. Look at one more constant of motion, which is px py plus m square omega square times xy divided by 2m. This is also a constant of motion. How do I check that? All that I have to do is check for A12 and the Hamiltonian. This is equal to 0. Okay? I will leave it for you people to check this, that A12 commuted Poisson bracket with edge is 0. So, this is also another constant of motion. Now, the phase space is 4 dimensional. How many independent independent constants of motion we are expecting? 3. Suppose there is a motion, then I can have at most 3 independent constants of motion. Remember, you can also think of it like this: a constant of motion, that means some generator is constant, but generator is an expression in the canonical variables. So, it is like a function of canonical variables is constant. What does that give you? A hypersurface or a surface. And then you have 3 of these. Remember, when you have 3 surfaces intersecting with each other, what you are left with is a curve, and that in fact is a curve along which your system is going to travel. You can't have 4 of them. If you have 4 of them, then your trajectory is just a point. Remember, we have done this in the first lecture again. If I can find 4 of them, I can find coordinate system where I find all 4 constants of motion, then the point stays standstill. But that is not the case here. Here the trajectory is a curve, in which case I have only 3 independent constants of motion, but I have listed 5 of them here, which means not all 5 are independent of each other. I should be able to express 2 of them in terms of remaining 3, or I must have 2 equations connecting 5 of them. So, here is one equation, that is clearly hx plus hy is nothing but h. So, this plus this is this, okay. And then the other one is L square. Of course, you have to expand everything and check that this identity holds, that L square plus A12 square plus A11 minus A22 square is also equal to h square by omega square. So, I had 5 listed quantities there, out of which because of 2 equations only 3 are independent, and that is what we were expecting. Now, what kind of transformations these constants of motions when treated as generators would generate? That is very easy to see. If I look at the solution, then x of t is simply a times sin omega t plus theta 1 and y of t is b times sin of omega t plus theta 2. I can express the 4 constants there a, b and theta 1, theta 2 in terms of the constants of motion, and that can be easily done. Remember, what is the energy here in the x degree of freedom? If this constant is a, then half m omega square capital A square is equal to the total energy in this, and that we know is exactly equal to A11. So, your capital A can be written as, or this is 2 times Hx by m omega square. Similarly for B, and similarly I can calculate A12 and associate that A12 with the phase difference between the 2 degrees of freedom. So, both are harmonic motions and there is a phase difference between the two. So, cos theta 1 minus theta 2 is related to your A12. Now, let us look at what kind of transformations they are generating. What does A11 do? So, A11, let me calculate delta x. Delta x is nothing but partial of h with respect to px, but that would simply give you alpha times px by m. Okay. Now, what about delta px? Delta px will be minus alpha times partial of h with respect to x, and that gives me alpha times m omega square, m square omega square x by m. Now, how do I look at this? So, this is similar to the rotation, but with slight difference. Remember, in the rotation, if I had x and px, if I do a rotation, simple rotation, then delta x would be proportional to px and delta px will be proportional to minus of x. That is exactly what you see here. You see, delta x is proportional to px and delta px is proportional to minus x. This is not exactly a rotation, but something similar. It is an elliptic transformation. Okay. So, x and px are getting intermixed. What about delta py, delta y and delta py? In this case, delta y here, delta y would be 0 and delta py also will be equal to 0. Okay. What does A22 do? Same thing, but for y coordinate and py coordinate. Okay. So, y and py. So, it is like a generating some sort of a elliptic rotation in y py plane. The first one was rotation in x px plane. What does h do? Both of them. So, it is a simultaneous rotation of x px and y py. What does your A12 do? A12 is a tricky one. It will transform or it will rotate x py plane. Remember, think of this as a 4-dimensional geometry. So, you have x py plane and y px plane. The A12 generates a rotation between these 2 planes. Okay. Rotation in each of these planes, but simultaneously. And finally, L rotation, of course, we know L rotation is just x and y plane is rotated and px py rotates at the same time, of course. So, these are the symmetry operations for this particular case. Now, let me look at the structure. So, these are generators and all possible multiplications of these generators will generate the main symmetry group. And what would be structure of that symmetry group? That would be really interesting to see. So, what I am going to do here is I am going to write these generators. Remember, the generators form a vector space. So, if I am given 2 generators, I can take a linear combination of these 2, construct another generator. So, it is all infinitely many possibilities are there. But how many independent generators? 3. Those are the basis vectors of your vector space. I am going to choose those 3 in a following way. So, let S11 be 1 over 2 omega times A12 plus A21. That is just basically A12 by omega. Okay. Let me define S2 in the same way, but it is A22 minus A11 by 2 omega, and S3 I am going to use L by 2. Okay, so basically what we have done is taken a linear combinations of A11, A12 and L, okay, and A22 of course. So these are all the 3 generators. All other generators can be written as linear combinations of these 3. And what kind of algebra this would generate is a question. So of course we can verify this. Remember the identity which I wrote couple of slides ago, that exactly is this identity here. Now calculate the Poisson brackets of S1, S2, S3 and show that it comes to this. The structure constants there. Here the summation over k is implied, but I will write it again. The structure constants here are again Levi-Civita symbols. What does this mean? The algebra of this is in fact isomorphic to the algebra of SO3, which was a symmetry group for a 3-dimensional system or some system in 3 dimensions which is spherically symmetric. You see, now we have found that the symmetry group of 2-dimensional harmonic oscillator is also similar to that of the SO3. Okay. So this is how you basically have to find the symmetry groups of the systems. Now the typical program of course would be something like this. It is not very easy to or obvious to see the symmetry group of a given system. Even in this case it was not very obvious. Remember, one of the rotation L is obviously seen because the potential has that particular symmetry, but other than that the remaining 2 generators and that they have same structure would be not very obvious, at least to me. So the idea here is when you have a system, it would help a lot in solving that problem if you could identify as many constants of motion as possible. And can you get them by looking at the system and the symmetries that the particular system possesses. So this of course is a hard problem, but it does help you in solving problem. Even if you do not find all the symmetries, whatever symmetries that you find immediately translates into constant of motion, and then the problem becomes easier. Okay. So this way this is where I will stop in this week. In the next week we are going to do Hamilton-Jacobi theory for the mechanical systems.